In mathematical order theory, an ideal is a special subset of a partially ordered set. Although this term historically was derived from the notion of a ring ideal of abstract algebra, it has subsequently been generalized to a different notion. Ideals are of great importance for many constructions in order and lattice theory. Basic definitions. A non-empty subset I of a partially ordered set is an ideal if the following conditions hold. For every x in I, yx implies that y is in I. For every x, y in I, there is some element z in I, such that x, z and y, z. While this is the most general way to define an ideal for arbitrary posets, it was originally defined for lattices only. In this case, the following equivalent definition can be given. A subset I of a lattice is an ideal if and only if it is a lower set that is closed under finite joins, i.e., it is non-empty and for all x, y in I, the element x, y of P is also in I. The dual notion of an ideal, i.e., the concept obtained by reversing all and exchanging with, is a filter. Some authors use the term ideal to mean a lower set, i.e., they include only condition 1 above. With this weaker definition, an ideal of a lattice seen as a poset is not closed under joins, so it is not necessarily an ideal of the lattice. Wikipedia uses only ideal, filter, and lower, upper set to avoid confusion. Frink ideals, pseudoideals and Euler pseudoideals are different generalizations of the notion of a lattice ideal. An ideal or filter is said to be proper if it is not equal to the whole set P. The smallest ideal that contains a given element P is a principal ideal, and P is said to be a principal element of the ideal in this situation. The principal ideal P for a principal P is thus given by P equals x in P, xP. Prime ideals. An important special case of an ideal is constituted by those ideals whose set theoretic complements are filters, i.e., ideals in the inverse order. Such ideals are called prime ideals. Also note that, since we require ideals and filters to be non-empty, every prime ideal is necessarily proper. For lattices, prime ideals can be characterized as follows. A subset I of a lattice is a prime ideal, if and only if I is a proper ideal of P, and, for every elements x and y of P, x, y in I implies that x is in I or y is in I. It is easily checked that this is indeed equivalent to stating that P I is a filter. For a complete lattice, the further notion of a completely prime ideal is meaningful. It is defined to be a proper ideal I with the additional property that, whenever the meet of some arbitrary set A is in I, some element of A is also in I. So this is just a specific prime ideal that extends the above conditions to infinite meets. The existence of prime ideals is in general not obvious, and often a satisfactory amount of prime ideals cannot be derived within ZF. This issue is discussed in various prime ideal theorems, which are necessary for many applications that require prime ideals. Maximal ideals. An ideal I is maximal if it is proper and there is no proper ideal J that is a strictly greater set than I. Likewise, a filter F is maximal if it is proper and there is no proper filter that is strictly greater. When a poset is a distributive lattice, maximal ideals and filters are necessarily prime, while the converse of this statement is false in general. Maximal filters are sometimes called ultrafilters, but this terminology is often reserved for Boolean algebras, where a maximal filter is a filter that contains exactly one of the elements A for each elementer of the Boolean algebra. In Boolean algebras, the terms prime ideal and maximal ideal coincide, as do the terms prime filter and maximal filter. There is another interesting notion of maximality of ideals. Consider an ideal I and a filter F such that I is disjoint from F. We are interested in an ideal M that is maximal among all ideals that contain I and are disjoint from F. In the case of distributive lattices, such an M is always a prime ideal. A proof of this statement follows. Proof. Assume the ideal M is maximal with respect to disjointness from the filter F. Suppose for a contradiction that M is not prime, i.e., there exists a pair of elements A and B such that AB in M but neither A nor B are in M. Consider the case that for all M in M, MA is not in F. One can construct an ideal N by taking the downward closure of the set of all binary joins of this form, i.e., N equals X MA for some M in M. It is readily checked that N is indeed an ideal disjoint from F which is strictly greater than M. But this contradicts the maximality of M and thus the assumption that M is not prime. For the other case, assume that there is some M in M with MA in F. Now if any element N in M is such that NB is in F, one finds that B and A are both in F, but N their meet is in F and, by distributivity, is in F too. On the other hand, this finite join of elements of M is clearly in M, such that the assumed existence of N contradicts the disjointness of the two sets. Hence all elements N of M have a join with B that is not in F. Consequently one can apply the above construction with B in place of A to obtain an ideal that is strictly greater than M while being disjoint from F. This finishes the proof. However, in general it is not clear whether there exists any ideal M that is maximal in this sense. Yet, if we assume the axiom of choice in our set theory, then the existence of M for every disjoint filter ideal pair can be shown, in the special case that the considered order is a Boolean algebra. This theorem is called the Boolean prime ideal theorem. It is strictly weaker than the axiom of choice and it turns out that nothing more is needed for many order theoretic applications of ideals. Applications. The construction of ideals and filters is an important tool in many applications of order theory. In Stone's representation theorem for Boolean algebras, the maximal ideals are used to obtain a set of points of a topological space, whose clopine sets are isomorphic to the original Boolean algebra. Order theory knows many completion procedures to turn posets into posets with additional completeness properties. For example, the ideal completion of a given partial order P is the set of all ideals of P ordered by subset inclusion. This construction yields the free DCPO generated by P. An ideal is principal if and only if it is compact in the ideal completion. So the original poset can be recovered as the subposet consisting of compact elements. Furthermore, every algebraic DCPO can be reconstructed as the ideal completion of its set of compact elements. History. Ideals were introduced first by Marshall H. Stone, who derived the name from the ring ideals of abstract algebra. He adopted this terminology because, using the isomorphism of the categories of Boolean algebras and of Boolean rings, the two notions do indeed coincide. Literature. Ideals and filters are among the most basic concepts of order theory. See the introductory books given for order theory and lattice theory, and the literature on the Boolean prime ideal theorem.